Okay, we're going to talk about a very important distribution in statistics called the standard normal distribution. It's also known as the Gaussian distribution, but ironically it was first discovered by de Moivre in work on the central limit theorem. So like many things in science, it seems to be named after the wrong person. So this is very important in statistics because of the central limit theorem and because so many distributions we will learn later in the course. When you sample the mean, your properties of how the mean, your estimate of the mean varies around the true mean will become a Gaussian distribution. So we do this all the time, and so the Gaussian distribution pops up all the time. And so this is something that we'll see throughout the rest of the class, and it has a formula. So the standard normal distribution, the general Gaussian distribution has a formula that says that the probability density is 1 over the standard deviation times the square root of 2 pi with a Gaussian. So this exponential of minus x minus mu squared over 2 times the variance. So the range is from minus infinity to infinity. Okay, so these tails extend on to infinity in both directions, and that will come up in another couple of lectures. Okay, so this is a sort of picture of what a Gaussian looks like along the x-axis. It's centered on its mean, and it has different quartiles, we call these, of the first standard deviation, second standard deviation, etc., going out from the mean. The area underneath this distribution, if you look at the mean plus or minus 1 standard deviation, that comprises 68% of the area. The mean plus or minus 2 standard deviations comprises 95% of the area. And the mean plus or minus 3 standard deviations is 99.7% of the area underneath the curve. Okay, so notice that the mean and the variance are just parameters in the distribution, and it's very common to make the variance, it's very common to make that 1, and the mean to shift it so that it's 0. And when we do that, we obtain the standard normal distribution, and that is for the random variable z, which is the original random variable minus the mean renormalized by the standard deviation. Okay, so this one has a probability distribution, or probability density, that is 1 over the square root of 2 pi exponential of minus 1/2 z squared. And again, z now takes values from minus infinity to positive infinity. Okay, so the cumulative distribution for the Gaussian is just like we've defined it before. It's the probability that z takes a value less than some z, so we're looking at the area under the curve up to some specific value of z. And we write that using our double barred p of z is by definition the integral from minus infinity up to z of the standard normal variable integrated over z. Okay, so you can write that in terms of the error function, 1/2 of 1 plus erf of z over square root of 2, where erf, the error function, is square root of 2 pi integrated from 0 up to some value x, e to the minus z squared dz. Okay, so that is the definition of erf. You can see where the square root of 2 comes in here because there's an exponential of minus z squared here, and our distribution depended on the exponential of minus 1/2 z squared. So we have to include this square root of 2 to account for that. So this is how you can find this result tabulated for different values of z in any textbook on probability. You can, of course, plug this one into your scientific calculator and thereby get that table directly out of your calculator without having to go and consult the table. Okay, so let's do an example calculation. We're going to suppose that we have measurements of a current flow and that those measurements take values that follow a normal distribution with a mean current of 10 milliamps and a variance of 4 squared milliamps. Okay, so what is the probability that a measurement will exceed 13 milliamps? Okay, so we have a variance that's 4 milliamps squared. That says our standard deviation is 2 milliamps, and we have a standard normal variable now that we can write down. That is x minus mu over sigma. In this case, the standard normal variable that we care about is 13. That's the value. We want to know if a measurement will exceed 13 milliamps. So we take 13 minus the mean and rescale by the standard deviation. And that gives us a z that should be greater than or equal to 1.5. Okay, so the question asks, what is the probability that z is greater than 1.5? And that, by definition, is 1 minus the probability that z is less than 1.5. Okay, so these are the tabulated things. These are the cumulative distributions, cumulative probabilities for different values of z. And of course, the probability that it's less than 1.5 added to the probability that it's greater than 1.5 is equal to 1. Okay, so that's where we get this equation for the probability that it's greater than 1.5. So we can look this up now. We have 1 minus the cumulative probability up to 1.5 for z is 0.93319. That I got from the appendix of table 2 in your textbook, Montgomery and Runger. And so that probability that in the question comes out to be 0.06681. Okay, we could have equally plugged this into our calculators using the error function. We would have gotten just 1 minus 1/2 of 1 plus ERF of 1.5 over 2. So there's a few steps to do that calculation, but you could do that using Excel or Mathematica. Okay, so now let's do another example. Let's ask, what's the probability that a measurement comes out to be between 9 and 11 milliamps? So we have now a lower bound and an upper bound, and we want to calculate the area underneath the standard normal variable when we shift that standard normal variable appropriately. Shift and rescale. Okay, so we've got z min is 9 minus 10 over 2, and that's minus 1/2. So that's a point along this z-axis that we're going to start our integration. And then the point of the maximum of this interval is going to be 11 minus 10 over 2, which is plus 1/2. So we're going to integrate z from minus 1/2 to 1/2 and look for the area underneath this, this standard normal curve. Okay, so that's saying the probability that you have z min less than z max. I could write that this way, right, as an integral of the probability density from z min up to z max. But I could also write that in a form that I can use to just look in the tables. Okay, so let's represent this specific interval as a difference between the integral from minus infinity up to z max. So that's going from here all the way up to here. Is representing z max in this formula. I'm going to subtract away the integral from minus infinity up to z min. That's going from minus infinity up to this point. And when I take the difference of those two, I've got this little sliver in between z min and z max. Okay, so that's what we really wanted to do. And the advantage of doing things this way is that I can look up this number and this number in the tables, right? This is a cumulative probability up to z max minus the cumulative probability up to z min. Okay, so that's what we have here, and those are 0.691 minus 0.308, and that comes out to 0.383. Okay, so that's the probability that we were asked to find. That a current is between 9 and 11 when the mean is 10 and the standard deviation is 2. Okay, so let's do yet one more example of using the Gaussian distribution. Here we're going to ask, what current is greater than 98% of all current measurements? Okay, so this question is a little bit different. Now we're given the area under the curve, and we want to find the point along the axis that corresponds to that limit, right? So we want to ask for what z is the cumulative probability up to z equal to 0.98. Okay, so we can go to table 2 in the appendix again and scan down through values for different values of z and look for one that comes up to just being 0.98. And the closest I could get in the table was z less than 2.05 is equal to 0.97982. Pretty good. Okay, we could use the error function. It does have an inverse, and we would be able to use that to find this value. But anyway, that's good enough for our purposes. And so we have z equals 2.05. We have to convert that now to specific values of the current using the known mean and standard deviation for this variable. Okay, so when z is equal to 2.05, then that's going to give us some value for x minus mu over sigma. Plugging in the mu equals 10 and sigma equals 2 milliamps, and then solving for z, we find that x equals 2.05 sigma plus mu, which comes out to be 14.1 milliamps. And so that's it. That's an example of, those are 3 examples of using the Gaussian distribution in various different ways.